Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches between stars, where ancient objects drift in silence for millions of years before gravity pulls them toward our sun. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the void between stars, there exists a population of wanderers that astronomers estimate numbers in the trillions rocky fragments and icy bodies ejected from their birth systems eons ago, now drifting through the galaxy's spiral arms at velocities measured in dozens of kilometers per second. These interstellar nomads carry within their frozen cores the chemical signatures of stellar nurseries that may no longer exist, preserving samples of cosmic evolution in their unaltered surfaces like geological time capsules wrapped in ice and stone. The space they traverse appears empty to human perception, yet contains roughly 1 hydrogen atom per cubic centimetre, a density so sparse that the best laboratory vacuum chambers on Earth seem crowded by comparison. The mathematics of their existence defies casual comprehension. A typical interstellar object might measure several hundred metres across, yet it travels through a medium so tenuous that collision with even a grain of interstellar dust becomes a noteworthy event. These wanderers experience temperatures hovering around 2.7 Kelvin, the background temperature of the universe itself, a cold so profound that molecular motion nearly ceases entirely. Their surfaces, sculpted by eons of cosmic ray bombardment, develop a dark, organic, rich crust that astronomers term space weathering, though the process unfolds over timescales that render human concepts of weathering almost quaint. What remains mysterious to planetary scientists is the precise mechanism by which these objects maintain their structural integrity across such vast timescales. Millions of years of exposure to cosmic radiation and micrometeorite impacts should theoretically erode them to dust, particularly the smaller fragments that lack sufficient gravity to hold their debris. Yet they arrive at stellar systems largely intact, their original mineralogy preserved beneath those darkened outer layers. Some theoretical models suggest that the extreme cold acts as a preservative, slowing chemical reactions and maintaining molecular bonds that would decay rapidly under warmer conditions. The irony settles quietly across these cosmic distances. Objects smaller than terrestrial mountains survive journeys that span gulfs our fastest spacecraft would require tens of thousands of years to complete. They drift in darkness colder than any earthly winter, carrying no memory of the warmth they once knew orbiting distant suns, no record of the planetary systems that ejected them into the galactic wilderness. Only the patient mathematics of celestial mechanics guides their paths. Invisible threads of gravitational influence that stretch across light years like a cosmic web designed to capture the next visitor drawn toward our solar neighbourhood. The nearest star to our Sun, Proxima Centauri, lies 4.24 light-years away, a gulf so vast that these wandering bodies spend most of their existence in true interstellar space, beyond the gravitational influence of any stellar system. Light from Proxima, travelling at the universe's ultimate speed limit, requires more than 4 years to bridge this distance. An interstellar object drifting at typical velocities of 20 to 30 kilometers per second would need roughly 40,000 years to traverse the same space. Assuming it travelled in a perfectly straight line without gravitational deflection, during these extended journeys through the galactic medium, the objects accumulate layers of interstellar material on their surfaces, primarily hydrogen and helium, but also trace amounts of heavier elements forged in the nuclear furnaces of massive stars and distributed through space by supernova explosions. This accretion process occurs at rates measured in individual atoms per square centimetre per year. so slowly that the accumulated material would form layers thinner than a human hair over geological timescales. Yet this cosmic dust carries isotopic signatures that reveal the chemical evolution of our galaxy's spiral arm over millions of years. The population dynamics of interstellar objects remain largely theoretical, based on extrapolations from the few examples detected within our solar system. Current estimates suggest that at any given moment, several dozen interstellar visitors may be passing through the space between Mars and Jupiter, most too small and dark to register on our telescopes. These invisible travellers follow hyperbolic trajectories that will carry them back into the void, having borrowed only a brief gravitational acceleration from our Sun before returning to their wandering existence among the stars, occasionally, very rarely. One of these ancient travellers encounters the outer boundary of our solar system's gravitational sphere of influence, a region extending nearly 2 light-years from the Sun, where our star's gravity begins to whisper its invitation across the dark. This gravitational sphere, known as the Hill sphere, represents the domain where our Sun's influence dominates over the gravitational tides of the Milky Way itself. Objects entering this vast region begin to feel the gentle tug of solar gravity, their trajectories slowly bending toward the inner planets, where human instruments wait to record their passage. The transition from interstellar space to solar influence occurs gradually, almost imperceptibly. An object travelling at 25 kilometers per second would require nearly 3,000 years to cross from the Hill sphere's outer boundary to the orbit of Pluto, accelerating incrementally as solar gravity strengthens its pull. During this extended approach, the wanderer sheds its long isolation, becoming part of our solar system's dynamic environment for the first time in millions of years. Most of these visitors will pass through our solar system once, never to return. Their hyperbolic orbits carry enough velocity to escape solar gravity after a brief encounter with our local neighbourhood. Only the patient mathematics of orbital mechanics determines their paths equations first described by Kepler and Newton centuries ago. Mathematical relationships that govern the motion of everything from planetary rings to interstellar wanderers, drawn temporarily into our Sun's gravitational embrace. When gravity calls across the dark, it speaks in mathematics older than mountains, older than the collision that formed our moon, older than the condensation of our solar nebula from interstellar gas and dust. The gravitational constant, measured to extraordinary precision as 674 times 10 to the negative 11th cubic meters per kilogram per second squared, governs every interaction between massive objects in the universe, from the orbital dance of binary stars separated by light years to the subtle tug our Sun exerts on wandering ice balls still dozens of astronomical units away. This fundamental force operates without regard to composition, temperature, or origin, treating a fragment of ancient Oort cloud material with the same mathematical certainty it applies to the rocky worlds of our inner solar system. An interstellar visitor entering the outermost reaches of solar influence begins its transformation from galactic wanderer to temporary solar system resident through a process so gradual that its effects become measurable only across decades of observation, at distances exceeding 1,000 astronomical units, where 1 astronomical unit represents the average distance between Earth and Sun, roughly 150 million kilometers. The gravitational acceleration imparted by our star measures mere fractions of a meter per second squared. This acceleration seems negligible compared to Earth's surface gravity, yet applied consistently across thousands of years, it fundamentally alters the trajectory of objects that have maintained nearly constant velocities for millions of years of interstellar travel. The mathematics governing this gravitational capture follow elegant equations derived from Newtonian mechanics, modified by Einstein's general relativity for extreme cases involving very massive objects or very high velocities. For typical interstellar objects approaching our solar system, classical mechanics provide sufficient accuracy to predict their paths with extraordinary precision. These calculations reveal that an object entering our solar system's sphere of influence with an initial velocity of 25 km per second will accelerate to more than 40 kilometers per second by the time it reaches perihelion, its closest approach to the Sun, before decelerating back to escape velocity as it departs toward interstellar space. What remains puzzling to orbital dynamicists is the precise three-dimensional trajectory these objects follow during their approach, particularly how galactic tidal forces and the gravitational influence of Jupiter and Saturn affect their paths over extended timescales. The galaxy itself rotates, carrying our entire solar system around the galactic center at roughly 220 kilometers per second, creating subtle tidal effects that influence the motion of objects in the outer solar system. These galactic tides, while extremely weak compared to solar gravity, accumulate over the centuries required for an interstellar object to cross from the outer boundaries to the inner planets. Computer simulations modeling these complex gravitational interactions require supercomputers running for weeks to accurately predict the behavior of individual objects across such extended timescales. The computational challenge arises from what mathematicians call the n-body problem. Predicting the motion of multiple gravitationally interacting objects becomes exponentially more complex as additional bodies enter the calculation. Even a simplified model including only the Sun, Jupiter, Saturn, and the incoming interstellar object involves solving differential equations with no analytical solution, requiring numerical approximation methods that accumulate small errors across millions of computational steps. The irony emerges slowly across these vast distances and timescales objects that have travelled freely through space for millions of years, following nearly straight-line trajectories determined by their initial ejection velocities, suddenly find themselves subject to the complex choreography of planetary motion. A fragment of ice and rock that last felt gravitational acceleration during its violent expulsion from a distant planetary system now responds to the gravitational architecture of our solar neighborhood, its path bending according to the combined influence of gas giants whose existence it has never encountered. As the visitor approaches closer to our Sun, the gravitational acceleration increases according to the inverse square law, doubling the gravitational force each time the distance decreases by a factor of the square root of 2. This relationship, discovered by Newton through careful analysis of planetary motion, means that an object experiences 4 times stronger gravitational pull at half the distance, 16 times stronger at 1/4 the distance, and so forth. The mathematical elegance of this relationship masks the profound physical reality that gravity represents a curvature in space-time itself, as Einstein demonstrated in his general theory of relativity. The approaching object also begins to experience differential gravitational forces across its extent, what astronomers term tidal forces. These arise because the side of the object closest to the Sun feels slightly stronger gravitational pull than the side farthest away, creating internal stresses that can fracture weakly bound aggregates of ice and rock. Most interstellar objects possess sufficient structural integrity to survive these tidal stresses, having been selected by millions of years of cosmic travel that naturally eliminated the most fragile wanderers. Only the most cohesive fragments complete the journey from their origin systems to ours. The transformation from interstellar wanderer to solar system visitor occurs across timescales that dwarf human experience, yet represent mere moments in the cosmic lifetime of these ancient objects. A typical visitor spends perhaps 50,000 years crossing from the outer boundary of solar influence to its closest approach to our Sun, then another 50,000 years departing back into interstellar space. This century-long engagement with our solar system represents less than 1% of the time the object has spent travelling between stars, a brief gravitational encounter in an existence measured in millions of years. During this extended approach, the object maintains its original temperature of approximately 2.7 Kelvin until it ventures within roughly 10 astronomical units of the Sun, closer than Saturn's orbit. At these distances, solar radiation begins to provide more heating than the cosmic microwave background radiation that has maintained the object's temperature throughout its interstellar journey. This thermal transition marks another boundary in the visitor's transformation, as it begins to experience the warmth of our star for the first time in millions of years. The gravitational dance continues with mathematical precision, each increment of acceleration carefully governed by the fundamental laws that organize cosmic motion. The visitor falls toward our sun not in the sense of plummeting directly downward, but following a curved trajectory that balances its inherited velocity with the growing pull of solar gravity, tracing an elegant hyperbolic path through the three-dimensional architecture of our planetary system. The mathematics of orbital mechanics unfold through equations that Johannes Kepler first glimpsed in the early 17th century, watching Mars trace its elliptical path against the stellar background with a precision that suggested deeper geometric truths governing planetary motion. These mathematical relationships, later refined by Newton into his law of universal gravitation, describe hyperbolic trajectories with the same elegant certainty they apply to the elliptical orbits of planets and the parabolic paths of comets. For interstellar objects entering our solar system, the relevant mathematics involve eccentricity values greater than 1 geometric parameters that define open curves extending to infinity. Mathematical expressions of journeys that begin and end in interstellar space. The orbital elements that describe these hyperbolic trajectories require 6 parameters to specify completely the semi-major axis: eccentricity, inclination, longitude of ascending node, argument of periapsis, and mean anomaly at epoch. Each parameter carries physical significance that translates the object's three-dimensional motion through space into precise mathematical language. The semi-major axis, paradoxically negative for hyperbolic orbits, measures the curvature of the trajectory as it bends around our sun. The eccentricity, always greater than unity, quantifies how much the path deviates from a perfect circle. Values approaching infinity indicate nearly straight-line trajectories barely deflected by solar gravity. These calculations reveal that an interstellar object approaching with a velocity of 25 km per second at infinite distance will follow a hyperbolic trajectory with an eccentricity of approximately 1.4, assuming a periapsis distance of 2 astronomical units. The mathematical relationship between approach velocity and orbital eccentricity follows from conservation of energy, one of the fundamental principles governing all motion in the universe. Energy conservation requires that the sum of kinetic and gravitational potential energy remains constant throughout the object's journey, creating an invisible mathematical constraint that determines the precise shape of its path through our solar system. Computer algorithms solving these orbital equations employ numerical integration methods developed originally for artillery calculations during the Second World War, adapted for the vastly different scales of celestial mechanics. The Runge method, named after German mathematicians Karl Runge and Martin Kuter, provides a systematic approach for approximating solutions to differential equations that lack analytical solutions. These computational techniques divide the object's trajectory into millions of tiny time steps, calculating the gravitational forces and resulting acceleration at each instant, then integrating these accelerations to predict the object's position and velocity moments later. What confounds orbital dynamicists is the sensitivity of these calculations to initial conditions. Tiny uncertainties in the object's position or velocity when first detected can lead to dramatically different predicted trajectories months or years later. This phenomenon, mathematically related to chaos theory, means that precise long-term predictions require extraordinarily accurate initial measurements. An uncertainty of merely 1 meter per second in the object's velocity, smaller than a gentle walking pace, can translate to positional uncertainties of millions of kilometers by the time the object reaches the outer planets. The mathematical description of the object's acceleration involves vector calculus, with gravitational forces from the Sun and major planets combining according to the principle of superposition. Each planet contributes its own gravitational acceleration vector, pointing toward the planet's center with magnitude determined by the inverse square law. The Sun dominates these calculations for most of the object's trajectory, but Jupiter's massive gravitational field can significantly perturb the path of objects passing within several astronomical units of the giant planet. These perturbations follow the same mathematical laws, but their effects accumulate over time in ways that challenge even modern computational methods. The concept of specific orbital energy provides another mathematical lens for understanding interstellar trajectories. This quantity, measured in units of energy per unit mass, remains constant throughout the object's journey due to conservation laws. For hyperbolic orbits, the specific orbital energy is positive, indicating that the object possesses more than enough kinetic energy to escape solar gravity entirely. This mathematical condition distinguishes interstellar visitors from periodic comets, which possess negative specific orbital energies and remain gravitationally bound to our solar system. The irony embedded in these precise calculations is that they describe the motion of objects whose origins remain largely unknown. Applying mathematical certainty to wanderers whose histories span millions of years of untraceable cosmic travel, Newton's equations, formulated to explain the motion of planets observed from Earth, prove equally valid for describing the trajectories of visitors from distant stellar systems, suggesting fundamental mathematical principles that transcend the boundaries between solar systems and extend throughout the galaxy. Relativistic corrections to these calculations become necessary only for objects approaching very close to the Sun or travelling at significant fractions of the speed of light. For typical interstellar visitors, the effects of Einstein's general relativity amount to positional corrections of mere meters over the entire trajectory, negligible compared to observational uncertainties. This mathematical simplification allows astronomers to rely primarily on Newtonian mechanics, equations that Newton himself could recognize and understand despite their application to phenomena he never imagined. The mathematical tools for orbit determination were developed through centuries of astronomical observation, beginning with Tycho Brahe's precise measurements of planetary positions and culminating in modern computer algorithms capable of processing millions of observations simultaneously. These methods, known collectively as orbit determination, involve fitting mathematical models to observational data through least squares techniques that minimize the differences between predicted and observed positions. The resulting orbital solutions provide the mathematical foundation for understanding not only where these objects have been, but where they will travel after departing our solar system. The precision of these mathematical predictions allows astronomers to schedule observations months or years in advance. Knowing exactly when and where telescopes should point to capture images of approaching visitors, this predictive capability represents one of astronomy's greatest triumphs, the ability to forecast the positions of distant objects with accuracy measured in arcseconds. Angular measurements so small they correspond to the apparent size of a coin viewed from several kilometers away. The equations governing orbital motion connect the visible trajectories of interstellar objects to the fundamental physical laws organizing cosmic dynamics, revealing mathematical relationships that extend from the quantum mechanical interactions within atomic nuclei to the gravitational architecture of galaxy clusters. These mathematical principles operate without regard to human observation, governing the motion of interstellar wanderers through the silent precision of natural law. Comet 2I Borisov, originally designated C2019 Q4 and later reclassified as the second confirmed interstellar object to visit our solar system, established the observational protocols that astronomers now employ to identify and track visitors from beyond our stellar neighborhood. Discovered on August 30, 2019 by amateur astronomer Gennady Borisov using a 65-meter telescope he constructed himself at the Margot Observatory in Nochny, Crimea. This ancient wanderer carried within its nucleus materials that condensed from the disk surrounding a distant star billions of years ago. The comet's hyperbolic trajectory, with an eccentricity of 3.36, indicated an origin far beyond the gravitational influence of our Sun, making it only the second interstellar object detected after one Oumuamua's brief passage through our solar system in 2017. The designation system for interstellar objects reflects astronomical nomenclature conventions established by the International Astronomical Union. with the prefix I, distinguishing interstellar visitors from periodic comets and asteroids that belong permanently to our solar system. The number preceding the I indicates the order of discovery when Oumuamua arrived first, followed by 2e Borisov, and now astronomers await confirmation of 3i Atlas and whatever new object races toward perihelion alongside it. This naming system acknowledges the growing recognition that interstellar objects represent a distinct class of solar system visitors, temporary residents whose origins lie in planetary systems orbiting distant stars. Spectroscopic analysis of 2i Borisov revealed a composition remarkably similar to comets native to our own solar system, suggesting that the processes governing planetary formation operate with consistent results across different stellar neighborhoods. The comet's spectrum showed strong emission lines from diatomic carbon molecules and cyanide radicals, chemical signatures identical to those observed in Oort cloud comets that formed in the outer regions of our own solar nebula 6 billion years ago. This compositional similarity implies that the star-forming region, where Borisov's parent system condensed, contained similar abundances of carbon, nitrogen, and oxygen as the molecular cloud that gave birth to our Sun. Observations conducted throughout 2019 and early 2020 documented Borisov's behavior as it approached and departed perihelion at a distance of approximately 2 astronomical units from the Sun, unlike 1i Oumuamua, which exhibited no detectable outgassing despite its close solar approach. 2i Borisov developed a classic cometary coma and tail, as solar heating sublimated volatile compounds from its nucleus. This outgassing behavior provided crucial data about the internal structure and composition of interstellar cometary nuclei, revealing that these ancient objects retain substantial quantities of water ice, carbon monoxide, and other volatile compounds despite millions of years of exposure to cosmic radiation. What puzzled cometary scientists was the comet's production rate of gas and dust, which remained lower than expected for an object of its estimated size throughout most of its passage through the inner solar system. Theoretical models predicting sublimation rates based on the comet's distance from the Sun consistently overestimated the observed outgassing, suggesting that Borisov's nucleus possessed either a lower volatile content than typical solar system comets, or a surface layer of refractory material that insulated the interior ice from solar heating. This discrepancy highlighted the challenges of applying models developed for solar system objects to visitors whose formation and evolution occurred under potentially different conditions. The photometric observations tracking Borisov's brightness variations revealed a rotation period of approximately 7.3 hours, indicating that the nucleus maintained a relatively rapid spin throughout its journey. This rotation rate, combined with spectroscopic measurements of the outgassing asymmetry, suggested that the comet's nucleus possessed an irregular shape with distinct compositional variations across its surface. The rotational dynamics of interstellar objects provide clues about their formation mechanisms and the violent processes that ejected them from their parent systems. Though interpreting these clues requires understanding collisional and gravitational processes that occurred billions of years ago in distant planetary systems, the international campaign to observe 2i Borisov involved telescopes spanning the globe, from ground-based observatories in Chile and Hawaii to space-based instruments like the Hubble Space Telescope and the European Southern Observatory's Very Large Telescope. This coordinated effort produced the most comprehensive dataset ever assembled for an interstellar visitor, establishing observational techniques and data reduction methods that now serve as templates for studying subsequent interstellar objects. The collaborative nature of these observations demonstrated the global astronomical community's recognition that interstellar visitors represent unique opportunities to study materials and processes from beyond our solar system. The irony of Borisov's discovery lies in its detection by a single amateur astronomer using a modest telescope. While professional surveys designed specifically to detect such objects initially missed its significance, Borisov's keen observational skills and dedication to systematic sky surveys revealed what billion-dollar automated detection systems had overlooked, emphasizing that astronomical discovery still rewards patient observation and careful analysis of subtle changes in the night sky. His discovery inspired enhanced protocols for rapid follow-up observations of objects with unusual orbital characteristics, ensuring that future interstellar visitors would receive immediate attention from the global astronomical community. The legacy of 2I Borisov extends beyond its individual scientific contributions to establish the framework for interstellar object research as a distinct astronomical discipline. The techniques developed for determining its orbit, analyzing its composition, and modeling its physical properties now provide standardized approaches for studying the growing population of interstellar visitors detected by increasingly sophisticated sky surveys. These methods combine astrometric precision with spectroscopic analysis and photometric monitoring to extract maximum scientific information from objects that remain visible for only a few months before departing back into interstellar space. The comet's departure from our solar system in late 2020 marked the end of active observations, but its influence on astronomical methodology continues to shape how researchers approach each new interstellar detection. The comprehensive dataset assembled during Borisov's passage provides a baseline for comparison with future visitors, establishing observational standards that will guide interstellar object research for decades to come. This wandering emissary from a distant star system transformed our understanding of what lies beyond our solar neighborhood, revealing that the cosmos contains vast populations of ancient fragments carrying messages from stellar systems we may never directly observe. Detection in the digital observatory begins with photons that have travelled across interstellar space for months or years, carrying within their wavelengths the subtle signatures of reflected sunlight from objects smaller than city blocks moving against the fixed backdrop of distant stars. The Catalina Sky Survey, operated by the University of Arizona's Lunar and Planetary Laboratory, employs a 68-meter Schmidt telescope on Mount Lemmon to systematically scan the night sky, capturing digital images every few minutes across predetermined search patterns that cover thousands of square degrees each month. These automated observations generate approximately 500 gigabytes of image data nightly, creating an archive that grows by nearly 200 terabytes annually, while algorithms search for the faint moving points of light that indicate asteroids, comets, or potentially more exotic visitors from beyond our solar system. The computational challenge of identifying moving objects within this vast dataset requires sophisticated image processing algorithms that can distinguish genuine celestial motion from the various forms of noise and artifacts that plague astronomical imaging. Modern CCD cameras used in these surveys detect individual photons with quantum efficiencies approaching 90%. But they also register cosmic ray impacts, electronic noise, and scattered light from bright stars that can masquerade as faint moving objects. The software systems analysing these images must apply multiple filters to eliminate false detections, while preserving the genuine signals from objects whose apparent motion may span only a few pixels across images separated by hours. The Linear Survey, operated jointly by MIT's Lincoln Laboratory and the USS Air Force, contributes additional detection capabilities using two 1.0-meter telescopes located at Socorro, New Mexico. These instruments scan overlapping regions of the sky using slightly different observational strategies, providing redundant coverage that increases the probability of detecting fast-moving objects that might be missed by a single survey. The statistical challenge becomes apparent when considering that a typical night's observations might contain hundreds of thousands of stellar images, among which fewer than a dozen represent genuine moving objects, and only a tiny fraction of those possess the unusual orbital characteristics that indicate interstellar origin. Automated detection algorithms employ what computer scientists term track-linking mathematical methods for connecting individual detections of the same object across multiple images taken at different times. These algorithms must account for the complex motions that result from the Earth's rotation and orbital motion around the Sun, which cause apparent motion even for stationary background stars. The software calculates expected motion patterns for objects at various distances from Earth, then searches for sequences of detections that match these predicted trajectories within statistical tolerances that account for measurement uncertainties and atmospheric effects. What complicates these automated searches is the vast range of possible orbital parameters that interstellar objects might possess, making it difficult to design algorithms that can recognize all potential visitors without generating excessive numbers of false detections, unlike asteroids and comets native to our solar system, which follow predictable orbital families determined by their formation locations and dynamical evolution. Interstellar objects can arrive from any direction, with approach velocities ranging from barely above solar escape speed to several times that threshold. This parameter space is so large that exhaustive searches become computationally prohibitive, requiring sophisticated optimization techniques to balance detection sensitivity with processing efficiency. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, operates 4 telescopes distributed globally to provide continuous surveillance of the night sky from locations in Hawaii, Chile, and South Africa. This network's primary mission focuses on detecting potentially hazardous asteroids that might impact Earth, but its systematic observations also capture data on any unusual objects passing through the surveyed regions. The ATLAS system's rapid cadence observations, with typical revisit times of 1 to 4 nights, provide the temporal resolution necessary to distinguish fast-moving interstellar objects from the slower motion characteristic of main belt asteroids. The initial detection of an unusual object triggers a cascade of follow-up observations designed to refine the preliminary orbit determination and confirm the object's interstellar nature. Professional observatories worldwide maintain target of opportunity programs that can rapidly redirect their telescopes toward newly discovered objects of potential interest. These follow-up observations require careful coordination among multiple facilities to ensure adequate sky coverage as the object's motion carries it across different regions, visible from various geographical locations. The irony embedded in these detection systems lies in their reliance on technology designed primarily to identify threats to Earth. Yet they routinely discover ancient wanderers whose journeys began millions of years before human civilization emerged. The same algorithms that scan for potentially dangerous asteroids on collision courses with our planet also reveal fragments of distant worlds that pose no threat but carry invaluable scientific information about planetary formation processes in other stellar systems. These dual-purpose surveys demonstrate how astronomical research benefits from the practical motivations of planetary defense, creating observational capabilities that serve both scientific curiosity and species survival. Statistical analysis of survey detection rates suggests that interstellar objects pass through the inner solar system far more frequently than early estimates predicted, with current models indicating that 1 or more such visitors should be detectable at any given time for observers with sufficiently sensitive telescopes. The challenge lies not in the rarity of these objects, but in recognizing their unusual characteristics among the thousands of asteroids and comets detected monthly by automated surveys. This recognition requires sophisticated orbital analysis that can distinguish the subtle signatures of hyperbolic trajectories from the elliptical orbits of solar system natives. The digital archives maintained by these surveys preserve not only the successful detections, but also the vast quantities of observational data that initially appeared unremarkable, creating repositories that can be searched retroactively as new analysis techniques become available. Modern data mining algorithms applied to historical survey archives have revealed previously unrecognized interstellar candidates hidden within datasets, originally processed with less sophisticated detection methods. These archival searches extend the effective timeline of interstellar object discoveries backward into the pre-digital era of astronomical photography, when human observers examined photographic plates by eye to identify moving objects. The global network of amateur astronomers contributes additional detection capabilities through coordinated observational programs that complement the major professional surveys. These dedicated observers, equipped with increasingly sophisticated CCD cameras and computerized telescopes, provide essential follow-up observations that help confirm and refine the orbits of newly discovered objects. The collaborative nature of modern astronomy demonstrates how professional and amateur observers work together to maximize the scientific return from each interstellar visitor's brief passage through our solar system. Spectroscopy reveals ancient composition through the analysis of light that has bounced from the surface of interstellar visitors, carrying within its wavelengths the chemical fingerprints of materials that condensed from stellar winds and supernova debris in distant regions of our galaxy millions of years ago. When sunlight strikes these wandering objects, molecules and atoms in their surface layers absorb specific wavelengths corresponding to electronic transitions between energy levels, creating absorption lines that serve as cosmic barcodes identifying the chemical elements and compounds present in their ancient crusts. Modern spectrographs, employing diffraction gratings with thousands of lines per millimeter etched with nanometer precision, spread this reflected light into rainbow spectra, where trained astronomers can read the stories written in atomic physics across interstellar distances. The high-resolution Echelle spectrometer mounted on the Keck telescope atop Mauna Kea achieves spectral resolution exceeding 70,000, meaning it can distinguish wavelength differences smaller than 1 part in 70,000 sufficient precision to resolve individual absorption lines from specific isotopes of common elements like carbon, nitrogen, and oxygen. These isotopic ratios provide crucial clues about the nuclear processes that forged the heavy elements within these objects, revealing whether their constituent atoms were synthesized in the cores of massive stars during supernova explosions or through the slow neutron capture processes that operate within aging red giant stars. Each isotopic signature carries information about the galactic chemical evolution that occurred in the object's birth region, potentially billions of years before our own solar system formed. Observations of interstellar object spectra consistently reveal surface compositions dominated by organic compounds, complex carbon-based molecules that form through radiation-induced chemistry during millions of years of exposure to cosmic rays and ultraviolet starlight. These organic materials, known collectively as space weathering products, create the characteristically dark surfaces observed on most interstellar visitors, with geometric albedos typically measuring less than 0.04, meaning they reflect less than 4% of incident sunlight. This remarkable darkness exceeds even that of fresh asphalt or charcoal, indicating surface chemistry processes that efficiently absorb electromagnetic radiation across visible wavelengths. The spectroscopic detection of water vapor, carbon monoxide, and cyanide molecules in the comae of outgassing interstellar comets provides direct evidence about the volatile inventories preserved within their nuclei since formation. These molecular emissions, excited to fluorescence by solar ultraviolet radiation, produce characteristic emission lines that allow astronomers to measure gas production rates and determine the relative abundances of different volatile species. Surprisingly, the volatile compositions of interstellar comets closely match those of comets native to our own Oort cloud, suggesting that similar physical and chemical processes governed ice condensation in the outer regions of protoplanetary disks throughout our galactic neighborhood. What puzzles astrochemists is the apparent absence of certain expected molecular species in interstellar object spectra, particularly complex organic molecules that laboratory experiments predict should form readily under the radiation conditions experienced during interstellar travel. Theoretical models of radiation chemistry suggest that millions of years of cosmic ray bombardment should synthesize substantial quantities of polycyclic aromatic hydrocarbons and other complex organics, yet spectroscopic searches for these compounds have yielded mostly null results. This discrepancy hints at unknown chemical processes that either prevent the formation of these molecules or destroy them more rapidly than predicted by current models. Near-infrared spectroscopy, conducted using instruments sensitive to wavelengths between 1 and 5 micrometers, reveals absorption features attributed to various forms of water ice, including both crystalline and amorphous phases that form under different temperature and pressure conditions. The crystalline ice signatures observed in some interstellar objects indicate that their surfaces have experienced thermal processing at temperatures above 100 Kelvin, suggesting either formation in the warmer regions of their parent protoplanetary disks or subsequent heating during close encounters with other stellar systems during their interstellar journeys. These thermal histories, encoded in the ice crystal structures, provide rare direct evidence about the environments these objects have experienced across cosmic time. The Doppler shifts measured in spectral lines allow astronomers to determine the three-dimensional velocities of interstellar objects with extraordinary precision, revealing not only their motion relative to our solar system, but also their rotation rates and the direction of their rotation axes. These velocity measurements, accurate to better than 1 meter per second, enable orbital calculations that can trace the object's trajectories backward through space for millions of years, potentially identifying their stellar systems of origin. However, the chaotic nature of galactic dynamics and gravitational perturbations from passing stars make such backtracking increasingly uncertain over extended timescales. The irony embedded in spectroscopic analysis lies in its ability to reveal intimate details about objects whose origins remain fundamentally mysterious, determining their chemical compositions with greater precision than many terrestrial materials, while their formation locations and ages remain largely speculative. Modern spectrographs can detect absorption lines from trace elements comprising less than 1 part per million of an object's surface composition. Yet the basic questions of where and when these objects formed continue to challenge our understanding of galactic evolution and planetary system formation processes. Polarimetric analysis of reflected light provides additional constraints on surface texture and mineralogy, revealing information about grain sizes, porosity, and the degree of space weathering that has modified the original surface composition. The polarization signatures observed in interstellar objects typically indicate surfaces composed of fine-grained, porous materials with complex, irregular textures that scatter light preferentially in certain orientations. These surface properties develop over millions of years through micrometeorite bombardment and cosmic ray gardening processes that gradually pulverize the outermost layers into regoliths, resembling those found on airless bodies throughout our own solar system. Spectroscopic monitoring campaigns extending across multiple months reveal temporal variations in gas production rates and surface properties as interstellar comets approach and recede from perihelion. These time-variable observations document the progressive activation of different volatile reservoirs within the nucleus as solar heating penetrates to various depths, providing insights into the internal structure and thermal properties of these ancient ice and rock aggregates. The seasonal changes observed in spectral features mirror those seen in solar system comets, suggesting fundamental similarities in comet physics regardless of origin. The archive of spectra accumulated from multiple interstellar visitors begins to reveal patterns in composition and behavior that may distinguish objects originating from different types of stellar systems or galactic environments. These comparative studies, still in their infancy due to the small sample size, hint at correlations between spectroscopic properties and orbital characteristics that could eventually provide diagnostic tools for determining interstellar object origins based solely on observations made during their brief passages through our solar system. The race through planetary orbits unfolds across a three-dimensional arena spanning billions of cubic kilometers, where two ancient wanderers now follow converging hyperbolic trajectories calculated with the precision that orbital mechanics demands. Their velocities, measured against the backdrop of our solar system's stately planetary dance, exceed anything achieved by human spacecraft. The newer arrival approaches perihelion at 43 kilometers per second, while 3I Atlas maintains its predicted course at 38 kilometers per second. Both objects carrying kinetic energies that dwarf the total output of terrestrial power generation across human history. These speeds, seemingly modest when expressed in familiar units, represent significant fractions of solar escape velocity, the theoretical threshold that separates temporary visitors from permanent residents of our gravitational neighborhood. The orbital geometry places both objects on trajectories that will carry them through the inner solar system during the same approximate time frame, creating an unprecedented opportunity for comparative observations of interstellar visitors with potentially different origins and evolutionary histories. Their paths, while appearing to converge when projected onto two-dimensional star charts, actually maintain safe separation distances exceeding 10 million kilometers vast gulfs that eliminate any possibility of gravitational interaction between the objects themselves. Yet small enough on cosmic scales to allow coordinated observational campaigns using the same telescopes and instruments. Current ephemeris calculations indicate that the racing newcomer will reach perihelion approximately 12 days before 3I Atlas completes its closest approach to our Sun, with both objects achieving their maximum velocities within a temporal window spanning less than one Earth month. This synchronized arrival represents an extraordinary coincidence, given that interstellar objects typically visit our solar system with intervals measured in years or decades between detections. The probability calculations governing such simultaneous arrivals suggest odds approaching 1 in several thousand, making this dual passage a rare observational opportunity that may not recur for generations. The newer object's trajectory carries it through perihelion at a distance of 1.4 astronomical units from the Sun, placing its closest approach between the orbits of Earth and Mars, while 3I Atlas will pass within 0.8 astronomical units, venturing closer to our star than Venus ever approaches. These different perihelion distances reflect the object's distinct approach, velocities, and orbital inclinations, parameters that were established millions of years ago when gravitational interactions with their parent stars first set these wanderers on their interstellar journeys. The mathematical relationships governing orbital mechanics ensure that objects with higher approach velocities typically achieve closer perihelion passages, trading gravitational potential energy for increased kinetic energy according to conservation laws that operate throughout the universe. What intrigues orbital dynamicists is the apparent correlation between the object's approach, directions, and their estimated times of ejection from their parent systems, suggesting that both visitors may have originated from stellar systems located in similar regions of our galaxy's spiral arm structure. Galactic orbital calculations, accounting for the differential rotation of stellar populations around the galactic center, indicate that objects ejected from nearby star-forming regions several million years ago could plausibly arrive at our solar system during similar time frames. However, the uncertainties inherent in these calculations, compounded by gravitational perturbations from passing stars and giant molecular clouds, make definitive origin determinations extremely challenging. The object's relative velocities with respect to our solar system's motion through the galaxy provide additional clues about their potential birthplaces, with both visitors approaching from directions that align roughly with the solar apex, the direction towards which our Sun moves as it orbits the galactic center. This geometric relationship suggests that the objects may have originated from stellar systems that shared similar galactic orbits with our own, possibly members of the same stellar association or cluster that dispersed over hundreds of millions of years of galactic evolution. Such kinematic evidence, while circumstantial, offers one of the few available methods for constraining the origins of objects whose individual stellar birth systems remain forever unknowable. Ground-based observatories worldwide coordinate their observation schedules to maximize coverage as both objects traverse different regions of the sky, with telescope allocation committees prioritizing target of opportunity programs that can rapidly respond to the evolving visibility windows. The logistical challenges of observing two simultaneously active interstellar objects strain the capacity of major observatories, requiring careful scheduling to balance the competing demands of ongoing research programs with the unique scientific opportunities presented by these rare visitors. Professional astronomical organizations coordinate these observational campaigns through emergency protocols typically reserved for supernova discoveries or gamma-ray burst follow-up observations. The irony inherent in this cosmic race becomes apparent when considering that both objects have traveled for millions of years through the vast emptiness of interstellar space. only to arrive at our solar system during the brief historical epoch when human civilization possesses the technological capability to detect and study their passage. The temporal coincidence spans not only their simultaneous arrival, but also their observation during the few decades when digital astronomy has developed sufficient sensitivity to recognize interstellar visitors among the thousands of asteroids and comets detected annually by automated surveys. Amateur astronomers contribute crucial observations using modest telescopes equipped with CCD cameras, providing continuous monitoring that complements the scheduled observations at major research facilities. These dedicated observers, coordinating their efforts through online networks and astronomical societies, demonstrate how modern astronomy benefits from distributed observational resources that can provide nearly continuous coverage of rapidly changing phenomena. Their contributions become particularly valuable during periods when weather or technical problems affect professional observatories, ensuring that critical phases of the object's evolution receive adequate documentation. The photometric data accumulated from multiple observatories reveals distinct light curves for each object, with brightness variations that reflect their different rotation periods, surface properties, and outgassing behaviors as they respond to increasing solar heating. These comparative studies provide unprecedented insights into the diversity of interstellar object properties, suggesting that wanderers from different stellar systems may retain distinctive characteristics that reflect the varied conditions present during their formation billions of years ago. Spectroscopic observations conducted simultaneously on both objects reveal subtle compositional differences that hint at distinct formation environments or evolutionary histories, with one visitor showing stronger signatures of organic compounds while the other displays more prominent silicate absorption features. These compositional variations, measurable through precise wavelength analysis of reflected sunlight, provide direct evidence that interstellar space contains representatives from multiple stellar populations with different chemical abundances and planetary formation processes. Outgassing and the comet's tail begin to manifest as the approaching interstellar visitor crosses the invisible threshold where solar radiation intensity exceeds the thermal equilibrium established during millions of years of interstellar travel, triggering sublimation processes that have remained dormant since the object's ejection from its distant parent system. At distances approaching 5 astronomical units from our Sun, roughly equivalent to Jupiter's orbital radius, the surface temperature of dark, organic, rich materials begins to rise above the critical threshold of approximately 150 Kelvin, where water ice transitions directly from solid to vapor without passing through a liquid phase. This sublimation process, governed by the Clausius-Clapeyron equation relating vapor pressure to temperature, releases water molecules that had remained frozen in crystalline lattices for geological ages, carrying with them embedded dust grains and organic particles that create the characteristic fuzzy appearance astronomers term a coma. The physics governing cometary outgassing follows well-established thermodynamic principles, yet each interstellar visitor displays unique behavioral patterns that reflect its individual composition, internal structure, and thermal history. Gas molecules sublimating from the nucleus expand rapidly into the near-vacuum environment surrounding the comet, achieving velocities of several hundred meters per second as they escape the weak gravitational field of the relatively small nucleus. These expanding gases carry embedded dust particles ranging in size from submicron grains to pebbles several centimeters across, creating a complex mixture of gas and solid particles that scatters sunlight to produce the visible coma observed through telescopes. Solar radiation pressure, arising from the momentum carried by photons streaming outward from our Sun at the speed of light, exerts differential forces on gas molecules and dust grains according to their size, composition, and optical properties. Smaller particles experience stronger acceleration relative to their mass, creating the characteristic separation between gas and dust components that produces distinct tail structures extending millions of kilometers behind the comet's nucleus. The ion tail, composed primarily of ionized gas molecules accelerated by the solar wind's magnetic field, points almost directly away from the Sun regardless of the comet's orbital motion. while the dust tail follows a curved trajectory that reflects the balance between solar radiation pressure and the comet's orbital velocity. Spectroscopic analysis of the expanding coma reveals the molecular inventory sublimating from the nucleus, with water vapor typically dominating the gas production, accompanied by smaller quantities of carbon monoxide, carbon dioxide, methane, and various organic compounds. The relative abundances of these species provide insights into the temperature and pressure conditions that existed during the comet's formation. As different volatile compounds condense from the gas phase at distinct temperatures within protoplanetary disks, surprisingly, many interstellar comets display volatile inventories remarkably similar to those of Oort cloud comets native to our solar system, suggesting that similar physical processes governed ice condensation in the outer regions of planetary systems throughout our galactic neighborhood. What confounds cometary scientists is the apparent delay between theoretical predictions of sublimation onset and the observed beginning of visible outgassing activity in many interstellar visitors. Models based on solar heating of idealized spherical nuclei predict that sublimation should commence when objects cross the 5 astronomical unit threshold. Yet observations often show significant delays before detectable coma development begins. This discrepancy suggests that interstellar comets may possess surface layers of refractory material formed through millions of years of cosmic ray bombardment and space weathering that insulate interior ice deposits from immediate solar heating. The outgassing process creates a feedback mechanism that can significantly alter the comet's orbital trajectory through what astronomers term non-gravitational forces. As sublimating gases expand asymmetrically from the rotating nucleus, they generate small but persistent rocket-like thrusts that can accelerate or decelerate the comet's motion depending on the orientation of active regions relative to the rotation axis. These non-gravitational accelerations, while tiny compared to solar gravity, accumulate over months of approach and departure, potentially altering arrival times by hours or days compared to purely gravitational orbit predictions. Photometric monitoring reveals that outgassing activity often exhibits pronounced variations correlated with the nucleus rotation period, indicating that volatile-rich and volatile-poor regions are distributed non-uniformly across the surface. These rotational-like curves provide indirect evidence about the nucleus shape and surface heterogeneity, revealing information about internal structure that cannot be obtained through direct imaging of objects too small and distant to resolve spatially. The rotation periods measured for interstellar comets typically range from several hours to several days, similar to those observed for solar system comets of comparable size. The irony of cometary outgassing lies in its destruction of the very materials that make these objects scientifically valuable, gradually eroding the pristine ancient ice that preserves chemical information about distant stellar systems, while simultaneously revealing the composition through spectroscopic analysis of the sublimated gases. Each passage through the inner solar system removes a measurable fraction of the nucleus mass, with typical mass loss rates ranging from thousands to millions of kilograms per second during peak activity periods. This irreversible process means that interstellar comets are literally consuming themselves to provide the observational data that makes their study possible. High-resolution imaging of active comets reveals complex jet structures where gas and dust escape preferentially from specific regions on the nucleus surface, creating collimated streams that extend hundreds of kilometers before dispersing into the broader coma. These jets often exhibit temporal variations that correlate with solar illumination patterns as the nucleus rotates, indicating that subsurface ice deposits become exposed and activated as different regions face toward our Sun. The jet morphologies provide clues about the nucleus' internal structure, suggesting a heterogeneous composition with distinct layers or pockets of volatile-rich material embedded within more refractory matrices. The developing tail structures create natural laboratories for studying fundamental plasma physics processes, as the solar wind, a stream of charged particles flowing outward from our Sun at velocities exceeding 400 km per second, interacts with the expanding cometary atmosphere. This interaction generates phenomena analogous to planetary magnetospheres, including bow shocks, magnetic field draping, and particle acceleration processes that operate on scales ranging from individual atomic interactions to structures spanning millions of kilometers. The detailed study of these plasma environments provides insights into similar processes operating throughout the solar system and in other astrophysical contexts. Gas production rates measured through spectrophotometry typically peak during perihelion passage, when solar heating reaches maximum intensity, then decline gradually as the comet recedes toward the outer solar system. However, many comets exhibit asymmetric activity patterns, with post-perihelion gas production sometimes exceeding pre-perihelion levels due to thermal lag effects as heat penetrates into the nucleus interior. These thermal models require sophisticated computational approaches that account for the complex geometry of irregular nuclear shapes, the thermal properties of mixed ice and rock compositions, and the three-dimensional heat diffusion processes that govern subsurface temperature evolution. Measuring time in astronomical units transforms the vast distances of interstellar space into manageable mathematical concepts, where one astronomical unit defined precisely as 149.97870, 7 kilometers. The average distance between Earth and our Sun provides the fundamental yardstick for describing planetary motions and the trajectories of visiting wanderers from distant stellar systems. Both racing objects now traverse regions of space where distances shrink from the hundreds of astronomical units that characterize the outer reaches of solar influence to the single-digit measurements that define the interplanetary realm, their velocities increasing according to the mathematical precision of Kepler's laws as gravitational potential energy converts to kinetic motion with perfect conservation of total mechanical energy. The newer interstellar visitor, currently positioned at 7 astronomical units from our Sun and approaching at a velocity that increases measurably each day, will reach its perihelion distance of 1.4 astronomical units in approximately 47 days, according to the most recent orbital calculations. These ephemeris predictions, updated continuously as new astrometric observations refine the trajectory parameters, achieve positional accuracy measured in hundreds of kilometers, despite predicting the location of an object millions of kilometers away weeks in advance. The mathematical foundation underlying these predictions rests on Newton's law of universal gravitation, modified by relativistic corrections that become significant only for objects passing within a few solar radii of our star's surface. Meanwhile, Thrus Atlas maintains its predetermined course toward a perihelion distance of 8 astronomical units, placing its closest solar approach well within the orbit of Venus at a distance where solar radiation intensity exceeds Earth's by a factor of more than 3. This proximity to our star will subject the comet's nucleus to surface temperatures potentially reaching 400 Kelvin, sufficient to drive vigorous sublimation of not only water ice, but also more volatile compounds like carbon monoxide and methane that remain stable at the greater distances where most cometary activity typically begins. The thermal models predicting these surface conditions must account for the complex interplay between absorbed solar radiation, infrared emission from heated surfaces, and the cooling effects of sublimating gases that carry away substantial quantities of thermal energy. The temporal convergence of both objects within the inner solar system creates observational opportunities measured in weeks, rather than the months or years typically available for studying individual interstellar visitors. Ground-based telescopes can simultaneously monitor both targets when they appear in the same region of the night sky, allowing direct comparison of their outgassing behaviors, spectroscopic properties, and photometric variations under identical observational conditions. This comparative approach eliminates many of the systematic uncertainties that complicate studies of objects observed at different times with different instruments under varying atmospheric conditions. What strikes orbital mechanicians as particularly remarkable is the precision with which these ancient objects follow their predicted trajectories. Despite having experienced millions of years of potential perturbations from stellar encounters, galactic tidal forces, and interactions with interstellar matter during their wandering existence. The mathematical elegance of gravitational dynamics operates with such consistency that orbits calculated from a few weeks of positional measurements can accurately predict locations months in advance, demonstrating the fundamental universality of physical laws that govern motion from subatomic particles to galactic superclusters. Current astrometric measurements place the newer visitor's position to within uncertainties of approximately 500 kilometers, a positional accuracy equivalent to pinpointing a basketball on a football field from a distance of several city blocks. This extraordinary precision results from combining observations made by multiple observatories worldwide, using statistical techniques that minimize random errors while accounting for systematic biases introduced by atmospheric refraction, instrument calibration uncertainties, and the finite speed of light that causes apparent positions to lag behind actual positions by amounts measurable in seconds for objects within our solar system. The decreasing distances from our Sun intensify solar radiation according to the inverse square law, creating exponentially increasing heating rates that drive progressively more vigorous outgassing as both comets approach their respective perihelion passages. At 2.7 astronomical units, the newer visitor receives solar irradiation approximately 7 times weaker than Earth experiences, while 3I Atlas, currently at 2 astronomical units, already experiences heating nearly equal to terrestrial values. These radiation levels trigger distinct phases of cometary evolution, with different volatile species beginning to sublime as temperature thresholds are crossed in sequence determined by their individual vapor pressure curves. The measurement of time itself takes on cosmic significance when expressed in astronomical units per day, the standard velocity unit employed in planetary astronomy that naturally accommodates the scales of solar system dynamics. The newer object currently moves at 0.85 astronomical units per day relative to our Sun, while 3I Atlas travels at 0.92 astronomical units per day, velocities that seem modest when expressed in these units, yet correspond to speeds exceeding 100,000 kilometers per hour. These velocity measurements, determined through precise Doppler analysis of spectral line shifts, achieve accuracies better than 1 meter per second despite measuring objects millions of kilometers distant. The irony embedded in these astronomical measurements lies in their translation of cosmic immensities into human-comprehensible scales, reducing the vast emptiness of interstellar space to numbers that fit comfortably within scientific notation, while preserving the mathematical relationships that govern planetary motion. An astronomical unit, defined by Earth's orbital radius, becomes the natural measuring stick for phenomena that dwarf terrestrial experience, creating a conceptual bridge between the familiar scale of human existence and the cosmic arena where these ancient wanderers complete their gravitational dance around our Sun. Photometric observations tracking brightness variations reveal rotational periods of 8.3 hours for the newer visitor and 7 hours for 3I Atlas, indicating that both objects maintain relatively rapid spins that likely reflect the violent processes that originally ejected them from their parent planetary systems. These rotation rates, combined with estimates of nucleus dimensions derived from thermal infrared observations, suggest rotation velocities approaching the breakup limit, where centrifugal forces would overcome the weak gravitational self-attraction, holding loosely consolidated ice and rock aggregates together. Spectroscopic monitoring campaigns document the progressive activation of different gas species as solar heating penetrates to various depths within the nuclear structures, revealing the complex thermal evolution that governs cometary behavior during solar system passage. Water vapor production rates increase exponentially with decreasing solar distance, following theoretical models that account for the temperature-dependent sublimation physics governing phase transitions between solid ice and gaseous water molecules in the near-vacuum environment surrounding cometary nuclei. The coordinated observations spanning multiple wavelengths from radio to ultraviolet create comprehensive data sets that capture the full range of physical processes occurring as these interstellar ambassadors respond to our Sun's gravitational and radiative influence. These multi-wavelength studies reveal phenomena invisible to single-color observations, including the complex chemistry occurring within expanding cometary atmospheres, where solar ultraviolet radiation dissociates molecules and ionizes atoms to create the exotic plasma environments that generate characteristic emission line spectra. The moment of perihelion passage arrives with mathematical inevitability. As both interstellar wanderers reach their closest approaches to our Sun within the precisely predicted timeframes calculated from months of orbital observations, their ancient trajectories culminating in encounters that represent the climactic moments of journeys that began millions of years ago in distant stellar systems. The newer visitor achieves perihelion at 4 astronomical units on a Tuesday morning at 03:47 Universal Time, while Thrus Atlas follows 12 days later. Passing within 0.8 astronomical units of our star's photosphere, at velocities that peak at 43.7 and 41.2 kilometers per second, respectively speeds that dwarf anything achieved by human technology, yet represent merely the natural consequence of gravitational acceleration operating across the vast distances of the inner solar system. At these closest approaches, both objects experience solar radiation intensities that exceed anything encountered during their interstellar wandering by factors of millions, transforming them from dormant ice and rock aggregates into actively outgassing comets, whose expanding atmospheres extend hundreds of thousands of kilometers into space. The surface temperatures on their sun-facing hemispheres climb rapidly past the sublimation points of water ice, carbon monoxide, and other volatile compounds, driving mass loss rates that can reach millions of kilograms per second as ancient materials preserved since planetary formation finally surrender to the thermal energy of our star's electromagnetic radiation. The gravitational acceleration experienced at perihelion reaches maximum values, determined by Newton's inverse square law, with both objects feeling solar gravity approximately 10 times stronger than Earth experiences from our Sun, creating tidal forces that stress their internal structures and potentially fragment any loosely bound components. These gravitational stresses, combined with the thermal expansion of heated materials and the outward pressure from sublimating gases, subject the nuclear structures to mechanical forces they have not experienced since their violent ejection from their parent systems eons ago. Observatories worldwide coordinate their observations to capture these critical moments when maximum outgassing activity reveals the most detailed information about nucleus composition and internal structure available during the entire passage through our solar system. High-resolution spectroscopy conducted during perihelion reveals emission lines from dozens of molecular species as solar ultraviolet radiation dissociates sublimating compounds and excites them to fluorescence, creating natural laboratories for studying astrochemistry under conditions impossible to replicate in terrestrial experiments. What fascinates planetary scientists is the remarkable similarity between the outgassing behaviors of these interstellar visitors and comets native to our own solar system, suggesting that fundamental physical processes governing ice sublimation and dust entrainment operate identically regardless of the stellar system where the objects originally formed. The gas production curves, relating sublimation rates to solar distance, follow nearly identical mathematical relationships for both interstellar and solar system comets, implying that similar volatile inventories and thermal properties characterize cometary nuclei throughout our galactic neighborhood. The peak heating rates at perihelion drive surface temperatures to levels where refractory materials begin to outgas, releasing compounds that normally remain stable except under extreme thermal conditions. Spectroscopic detection of metallic species like sodium, iron, and magnesium in the expanding comae provides direct evidence about the rocky components within the nuclear structures, revealing mineral compositions that formed during the earliest phases of planetary accretion in distant protoplanetary disks billions of years ago. Solar-wind interactions with the expanding cometary atmospheres reach maximum intensity during perihelion passage, as the dense plasma environment surrounding our Sun encounters the neutral gas and dust streaming from the nuclear surfaces. These interactions generate complex magnetohydrodynamic phenomena, including magnetic field draping, particle acceleration, and plasma instabilities that create the characteristic ion tails streaming millions of kilometers anti-sunward from both objects. The detailed study of these plasma physics processes provides insights into similar interactions occurring throughout the heliosphere and in other stellar wind environments. The enormous kinetic energies possessed by both objects at perihelion, calculated as 1/2 mass times velocity squared, exceed the total energy content of terrestrial nuclear arsenals. Yet this energy remains entirely gravitational in origin, accumulated through the patient operation of Newton's laws during the extended approach from interstellar distances. These energy levels, while staggering by human standards, represent typical values for objects following hyperbolic trajectories through stellar gravitational fields, demonstrating the immense energies involved in cosmic dynamics operating on planetary scales. The irony of perihelion passage lies in its simultaneous revelation and destruction of the ancient materials that make interstellar objects scientifically valuable. With maximum information content coinciding with maximum erosion rates, as sublimating gases carry away irreplaceable samples of primordial solar system analogues. Each moment of peak activity provides unprecedented insights into distant planetary formation processes, while simultaneously consuming the evidence through irreversible mass loss that reduces nucleus dimensions by measurable amounts during single perihelion passages. Thermal infrared observations conducted during closest approach reveal surface temperature distributions that map the three-dimensional shape and rotation state of the nuclear structures, providing indirect imaging capabilities for objects too small and distant to resolve spatially through conventional optical telescopes. These thermal mapping techniques, originally developed for studying asteroids and solar system comets, prove equally effective for characterizing interstellar visitors whose surface properties reflect millions of years of space weathering under cosmic ray bombardment and micrometeorite impacts. High-speed photometry captures rapid brightness fluctuations caused by rotating surface features and episodic outgassing events, revealing details about nuclear structure and composition heterogeneity on timescales ranging from minutes to hours. These temporal variations provide clues about internal layering, volatile distribution, and mechanical properties that govern how these ancient aggregates respond to thermal stress and gravitational torques during their brief encounters with intense solar heating. The gravitational slingshot effect becomes apparent as both objects round their respective perihelion points, gaining additional kinetic energy through the exchange of momentum with our Sun's orbital motion around the galactic center. This energy transfer, while imperceptible on solar scales, provides measurable acceleration to the departing visitors, ensuring that they will achieve velocities sufficient to escape our solar system entirely and resume their wandering existence among the stars. Radio observations detect synchrotron emission from relativistic electrons accelerated within the complex magnetic field structures surrounding the active comae, providing evidence for particle acceleration processes that operate throughout the cosmos wherever plasma environments interact with magnetic fields. These high-energy phenomena, detectable only with sensitive radio telescopes, reveal aspects of cometary physics invisible to optical observations, yet crucial for understanding the complete range of processes occurring during these brief but intensive encounters with stellar radiation and gravitational fields. The precise timing of perihelion passage, predicted months in advance through orbital calculations, demonstrates the remarkable accuracy achievable through gravitational dynamics, with actual passage times differing from predictions by mere minutes, despite the complex perturbations introduced by outgassing forces and planetary gravitational influences. This predictive precision enables coordinated observational campaigns that maximize the scientific return from each interstellar visitor's brief moment of maximum activity. Photographic evidence of ancient ice emerges through high-resolution imaging conducted during the visitor's closest approaches to our Sun, when enhanced solar illumination and proximity to Earth-based telescopes combine to reveal surface features that have remained unchanged since these objects' formation in distant protoplanetary disks billions of years ago. The adaptive optic systems employed by modern ground-based observatories, using deformable mirrors that correct for atmospheric turbulence hundreds of times per second, achieve angular resolution approaching the theoretical diffraction limit of large telescopes, enabling detection of brightness variations across nuclear surfaces smaller than typical city blocks, despite distances measured in hundreds of millions of kilometers. CCD cameras cooled to liquid nitrogen temperatures capture photons with quantum efficiencies exceeding 90%, preserving every available signal from these faint targets, whose apparent brightnesses barely exceed the detection thresholds of even the most sensitive astronomical instruments. Digital image processing algorithms enhance contrast and remove instrumental artifacts to reveal subtle albedo variations that reflect compositional heterogeneity across surfaces sculpted by eons of cosmic ray bombardment, micrometeorite impacts, and thermal cycling between the extreme cold of interstellar space and the modest warming experienced during rare encounters with stellar radiation fields. The photographic record documents distinct surface regions where water ice sublimates preferentially, creating the characteristic bright patches that astronomers associate with freshly exposed volatile rich materials beneath the dark, organic-rich crusts that develop through prolonged exposure to cosmic radiation. These albedo patterns provide direct evidence for the stratified internal structure theorized to exist within cometary nuclei, where pristine ice deposits remain preserved beneath protective layers of refractory materials that accumulated during millions of years of space-weathering processes. Polarimetric imaging, which analyzes the orientation of light waves reflected from different surface regions, reveals information about grain sizes, porosity, and mineralogical composition invisible to conventional photometry. The polarization signatures observed on both interstellar visitors indicate surfaces composed of fine-grained, highly porous materials with complex, irregular textures that scatter light according to principles governing electromagnetic wave interactions with particulate media. These scattering properties closely match those observed on asteroids and comets, native to our solar system, suggesting similar surface evolution processes operate regardless of formation location within our galaxy. What surprises planetary geologists is the apparent preservation of original surface features despite millions of years of exposure to the harsh environment of interstellar space, where cosmic ray particles and ultraviolet radiation from distant stars should theoretically erode and chemically alter exposed materials at measurable rates. Theoretical models of space weathering predict that unprotected surfaces should develop thick mantles of radiation-processed organics within timescales much shorter than typical interstellar transit durations. Yet observations reveal surface heterogeneity that implies recent exposure of underlying materials through unknown mechanisms. Multi-wavelength imaging spanning visible, near-infrared, and thermal infrared wavelengths creates composite color maps that highlight compositional variations across the nuclear surfaces, revealing patterns that suggest complex geological histories involving multiple episodes of volatile loss, impact cratering, and thermal processing. The color variations observed in these false color images correspond to different mixtures of water ice, organic compounds, and silicate minerals, providing insights into the original accretion processes that assemble these objects from smaller planetesimals within their birth planetary systems. Time-lapse photography documenting the development and evolution of outgassing jets reveals the precise locations where subsurface ice deposits become exposed to solar radiation, creating ephemeral features that persist for hours or days before fading as rotation carries active regions away from optimal solar illumination angles. These temporal sequences provide direct observational evidence for the three-dimensional structure of volatile reservoirs within the nucleus interiors, revealing information about internal layering and composition gradients that accumulated during the original formation processes billions of years ago. The photographic evidence includes detection of discrete particles ejected from the nuclear surfaces during episodic outgassing events, with individual dust grains occasionally visible as point sources that separate gradually from the main coma as they follow independent trajectories determined by their size, composition, and ejection velocities, High-speed imaging reveals the dynamics of these particle ejection processes, documenting how gas pressure from sublimating volatiles accelerates embedded dust grains to escape velocities that overcome the weak gravitational fields of the relatively small nucleus masses. The irony embedded in these photographic records lies in their documentation of materials that formed when these objects' parent stars were young, possibly before our own sun had fully settled onto the main sequence, preserving visual evidence of planetary formation processes that occurred during earlier epochs of galactic evolution. Each pixel in these digital images captures light that has bounced from surfaces potentially older than our entire solar system, carrying information about stellar nucleosynthesis, interstellar chemistry, and accretion disk dynamics that operated under conditions quite different from those present during our own planetary formation. Comparison between images taken weeks apart reveals measurable changes in surface topography, as sublimation erodes specific regions at rates determined by local composition and solar illumination geometry, providing direct observations of landscape evolution occurring on timescales accessible to human observation. These erosional processes, while extremely slow by terrestrial standards, operate rapidly enough during peak solar heating to alter surface features detectably between observing sessions, creating unique opportunities to study geological processes operating under low gravity, vacuum conditions impossible to replicate in laboratory settings. Photometric analysis of reflected sunlight reveals rotation periods and spin axis orientations for both objects, indicating that they tumble through space with complex rotational motions that may reflect the chaotic dynamics of their original ejection from planetary systems disrupted by stellar encounters or planetary migration events. The non-principal axis rotation observed in both cases suggests that these objects experience collisional or gravitational torques that imparted angular momentum vectors not aligned with their principal moments of inertia, creating the complex tumbling motions documented through careful analysis of brightness variations. High-resolution morphological studies reveal impact craters, linear features, and albedo boundaries that provide evidence for the geological processes that shape these surfaces during their extended residence in interstellar space, where collisions with interstellar dust grains and cosmic ray bombardment gradually modify surface properties through mechanisms that operate continuously but imperceptibly slowly. The preservation of fine-scale topographic features suggests that these erosional processes remain inefficient even over million-year timescales, implying that surface compositions possess sufficient cohesion to maintain structural integrity despite prolonged exposure to the harsh interstellar environment. Spectrophotometric mapping combines photographic imaging with wavelength-resolved analysis to create detailed compositional maps that reveal the distribution of different chemical species across the nucleus surfaces, providing insights into the original heterogeneity of materials that accreted to form these objects within their birth protoplanetary disks. These compositional maps reveal patterns that suggest radial and temporal variations in the volatile and refractory inventories available during different phases of planetary system formation, preserving evidence for the complex chemical evolution that occurred within distant stellar nurseries billions of years before our solar system existed. The slingshot effect takes hold with mathematical precision as both interstellar visitors round their respective perihelion points and begin their departure from the inner solar system, their trajectories fundamentally altered by the gravitational encounter with our Sun in ways that will influence their motion through the galaxy for millions of years to come. This gravitational assist, first described theoretically by Walter Hohmann in the 1920s, and later refined by aerospace engineers planning spacecraft missions to the outer planets, operates through conservation of energy and angular momentum as the objects exchange kinetic energy with our Sun's orbital motion around the galactic center, gaining velocity through a process that adds negligible perturbation to our star's massive bulk, yet provides substantial acceleration to these relatively tiny wanderers. The physics governing this energy transfer follows directly from Newton's laws of motion and gravitation, with the mathematical framework describing how objects following hyperbolic trajectories gain velocity proportional to the sine of their deflection angle and the escape velocity at periapsis. For the newer visitor, passing within 1.4 astronomical units of our Sun, theoretical calculations predict a velocity increase of approximately 3.7 kilometers per second, while 3I Atlas, venturing closer to 0.8 astronomical units, will gain roughly 5.2 kilometers per second during its gravitational encounter. These velocity increments, while seemingly modest compared to the object's initial approach speeds, represent substantial changes in kinetic energy that ensure both visitors will achieve sufficient velocity to escape our solar system entirely. The gravitational deflection angles experienced by both objects exceed 30 degrees, bending their trajectories significantly from the nearly straight-line paths they followed during their approach from interstellar space toward new directions that will carry them toward different regions of our galaxy's spiral arm structure. These deflections result from the cumulative gravitational influence experienced throughout their passages through the inner solar system, with the strongest effects occurring during the hours surrounding perihelion, when solar gravity reaches maximum intensity and the objects achieve their highest velocities relative to our Sun. What fascinates celestial mechanicians is the reversibility of these gravitational interactions, which operate identically regardless of the direction of time, meaning that the same mathematical equations describing the object's acceleration during approach also govern their deceleration during departure. The symmetry inherent in gravitational dynamics ensures that objects gain as much velocity during their inbound journey as they lose during their outbound passage, with the net energy change determined entirely by the geometry of their hyperbolic trajectories and the strength of gravitational coupling at periapsis. Current tracking data indicates that the newer visitor's post-perihelion trajectory will carry it toward a galactic longitude approximately 47 degrees different from its approach direction, while 3I Atlas will depart at an angle 63 degrees from its inbound path. These directional changes, while substantial when measured in degrees, translate to relatively small angular separations when projected across the vast distances of interstellar space, meaning both objects will likely remain within the same general region of our galaxy's local stellar neighborhood for millions of years following their solar encounters. The velocity vectors imparted by gravitational acceleration ensure that both objects will escape our solar system, with speeds exceeding the local galactic velocity dispersion, meaning they will travel faster relative to nearby stars than typical stellar motion within our spiral arm. This enhanced velocity will reduce the probability of future gravitational capture by other stellar systems, effectively ensuring that both visitors will continue their wandering existence as free-floating interstellar objects for the remainder of their cosmic lifetimes. Doppler shift measurements conducted during the departure phase reveal the precise three-dimensional velocity vectors with accuracies better than 1 meter per second, enabling detailed calculations of the object's future trajectories through local galactic space. These velocity determinations require careful correction for the Earth's orbital motion, solar system motion around the galactic center, and relativistic effects that become measurable for objects traveling at significant fractions of typical stellar velocities within our galaxy. The acceleration experienced during the slingshot maneuver subjects both objects to tidal forces that stress their internal structures according to the differential gravitational effects across their finite dimensions. While these tidal stresses remain well below the structural limits for coherent rocky or icy bodies, they can potentially fragment any loosely bound aggregates that lack sufficient internal cohesion to withstand the mechanical forces generated during close stellar encounters. Observations during and after perihelion reveal no evidence for fragmentation in either visitor, suggesting that both objects possess adequate structural integrity to survive gravitational encounters with solar mass stars. The irony of gravitational slingshot acceleration lies in its ability to impart substantial kinetic energy to departing objects without any expenditure of energy by our Sun, demonstrating how gravitational interactions can efficiently transfer momentum between astronomical bodies through purely conservative force interactions. This energy transfer represents a fundamental property of gravitational dynamics that operates throughout the universe. From the orbital evolution of binary star systems to the gravitational assist maneuvers employed by spacecraft exploring the outer solar system, post-perihelion spectroscopic observations reveal continued outgassing activity as both objects recede from our Sun, though with declining intensity as solar heating decreases according to the inverse square law governing electromagnetic radiation. The persistence of cometary activity well beyond perihelion provides extended opportunities for studying the internal structure and composition of these interstellar visitors, with spectral line ratios evolving as different volatile species freeze out in sequence determined by their individual sublimation temperature thresholds. Astrometric measurements tracking the object's positions relative to background stars achieve positional accuracies sufficient to detect the subtle acceleration effects of non-gravitational forces arising from asymmetric outgassing, revealing how rocket-like thrust from sublimating gases can measurably alter trajectories over timescales of weeks to months. These non-gravitational perturbations, while small compared to gravitational acceleration, accumulate to produce velocity changes comparable to those achieved by spacecraft propulsion systems, demonstrating the effectiveness of natural outgassing as a propulsion mechanism operating in the vacuum environment of space. The gravitational environment during departure becomes progressively simpler as both objects recede beyond the orbital distances of the major planets, transitioning from the complex multi-body dynamics of the inner solar system toward the nearly uniform gravitational field dominated entirely by our Sun's influence. This simplification allows increasingly accurate long-term trajectory predictions as perturbations from planetary gravitational fields fade below the threshold of observational detection, enabling precise calculations of the object's asymptotic velocities and departure directions. Radio tracking of both objects continues as they fade beyond optical detection limits, employing sensitive receivers that can detect the weak radar echoes reflected from their surfaces when illuminated by powerful planetary radar transmitters. These radar observations provide complementary measurements of distance and velocity that extend the baseline for orbital determination well beyond the time frame accessible to optical observations, improving the accuracy of trajectory calculations that will guide searches for similar objects in future sky surveys. Data transmission across light years begins with the careful encoding of measurements and observations into digital formats that can preserve the scientific information gathered during these brief interstellar encounters, transforming photons captured by telescope mirrors and electronic signals generated by spectrographs into numerical datasets that will outlast the objects themselves as they fade back into the cosmic dark. Radio telescopes around the globe coordinate their transmissions to broadcast these precious observations toward deep space monitoring stations and interstellar communication networks, encoding the chemical compositions, orbital parameters, and physical properties of both visitors into electromagnetic signals that propagate outward at the speed of light, carrying messages about our solar system's temporary guests toward civilizations that may exist around distant stars. The digital archives maintained by astronomical observatories worldwide accumulate terabytes of imaging data, spectroscopic measurements, and astrometric positions that document every observable aspect of both objects' passages through our solar system, creating comprehensive records that future researchers will analyze for decades using computational techniques not yet developed. These databases employ redundant storage systems and error correction algorithms that ensure the preservation of observational data across technological generations. Recognizing that interstellar visitors represent irreplaceable opportunities for scientific discovery that must be documented with maximum fidelity for posterity, sophisticated data compression algorithms reduce the storage requirements for high-resolution images and spectra while preserving all scientifically relevant information. Employing mathematical techniques that exploit the statistical properties of astronomical data to achieve compression ratios exceeding 100 to 1 without any loss of measurement accuracy. These compressed data sets can be transmitted efficiently across interplanetary distances using existing deep space communication networks, enabling the sharing of interstellar object data with space-based observatories and future missions to the outer solar system that may encounter additional visitors from beyond our stellar neighbourhood. What challenges data archivists is the development of storage formats and metadata standards that will remain accessible and interpretable across the decades or centuries required for comprehensive analysis of interstellar object properties. Given the rapid evolution of computing technology and data processing methodologies, current efforts focus on establishing open-source file formats and standardized calibration procedures that can be decoded by future astronomical software systems, ensuring that today's observations will enhance tomorrow's understanding of galactic dynamics, in planetary formation processes operating throughout our local stellar neighbourhood. The transmission protocols employed for interstellar data communication utilize error-correcting codes originally developed for deep space missions, employing redundant encoding schemes that can reconstruct complete messages even when significant portions are corrupted by cosmic ray interference or equipment failures during the extended transmission times required for interstellar distances. These mathematical techniques, based on algebraic number theory and information theory principles, provide reliable communication channels across the vast distances separating stellar systems within our galaxy's spiral arm structure. Automated data reduction pipelines process the raw observational measurements through calibration procedures that account for instrumental effects, atmospheric distortions, and systematic biases that affect ground-based and space-based observations differently. These processing algorithms apply flat-field corrections, wavelength calibrations, and photometric standardizations that transform the raw detector counts into physical measurements of brightness, velocity, and chemical abundance that can be compared directly with theoretical models and observations of similar objects. The scientific papers documenting these observations undergo peer review processes that ensure the accuracy and reliability of published results, with independent researchers verifying orbital calculations, spectroscopic identifications, and statistical analyses before the findings enter the permanent scientific literature. This quality control system prevents the propagation of erroneous measurements or incorrect interpretations that could mislead future research efforts. Maintaining the integrity of the observational record that forms the foundation for advancing our understanding of interstellar object populations and properties. International data sharing agreements facilitate the rapid distribution of observational results among research institutions worldwide, ensuring that the scientific community can coordinate follow-up observations and theoretical investigations, while the objects remain accessible to telescopic study. These collaborative protocols recognize that interstellar visitors represent global scientific resources that transcend national boundaries and institutional affiliations, requiring coordinated international efforts to maximize the scientific return from these rare cosmic encounters. The digital preservation of spectroscopic data employs multiple redundant storage systems distributed across geographically separated facilities, protecting against data loss due to natural disasters, equipment failures, or institutional changes that might threaten the long-term accessibility of irreplaceable observational records. Cloud-based storage systems and distributed computing networks provide additional layers of protection, while enabling global access to the complete datasets for researchers who lack access to major astronomical facilities. The irony embedded in these data transmission efforts lies in their attempt to preserve temporal observations of ancient objects, whose formation predates human civilization by billions of years, encoding fleeting measurements of cosmic wanderers into digital formats that may themselves become obsolete before the objects complete their next stellar encounters. The technological systems designed to capture and preserve these observations operate on timescales measured in years or decades, while the objects themselves exist on cosmic timescales that dwarf human technological development. Machine learning algorithms trained on the accumulated datasets begin to identify patterns and correlations invisible to traditional statistical analysis, revealing relationships between orbital parameters, compositional properties, and outgassing behaviors that provide insights into the formation and evolution of interstellar object populations. These artificial intelligence techniques complement traditional analytical methods by exploring high-dimensional parameter spaces that exceed human cognitive capabilities, potentially discovering new physical relationships governing interstellar object properties. Real-time data streaming enables amateur astronomers and educational institutions to access processed observations within hours of their acquisition, democratizing access to cutting-edge astronomical research and inspiring public interest in interstellar science. These outreach efforts recognize that scientific discovery belongs to all humanity, not merely to professional research institutions, and that public engagement enhances support for the observational programs that make interstellar object research possible. The transmission bandwidth requirements for sharing comprehensive datasets challenge existing communication infrastructure, particularly for high-resolution imaging and spectroscopic observations that generate data volumes measured in hundreds of gigabytes per observing session. Advances in data compression, network protocols, and satellite communication systems gradually improve the efficiency of scientific data distribution, enabling more rapid sharing of observational results among international research collaborations. Legacy planning for long-term data preservation addresses the challenges of maintaining accessible archives across multiple generations of computing technology. Developing migration strategies that can transfer datasets between evolving storage systems while preserving all metadata and calibration information essential for scientific interpretation. These preservation efforts recognize that interstellar object observations represent cultural as well as scientific heritage, documenting humanity's first systematic studies of visitors from distant stellar systems. The long journey to galactic dawn stretches ahead for both interstellar wanderers as they depart our solar system with enhanced velocities that will carry them through the sparse medium between stars for eons, measured against cosmic rather than human timescales. Their trajectory is now permanently altered by gravitational encounters that represent mere moments in existence as spanning millions of years. The newer visitor accelerated to 28, 4 kilometers per second relative to our Sun, will require approximately 140,000 years to traverse the distance to Proxima Centauri, our nearest stellar neighbour, though its actual trajectory carries it toward a different region of local galactic space, where no bright stars currently shine within several light-years of its predicted path. Meanwhile, 3i Atlas departs with an asymptotic velocity of 31, 7 kilometers per second, following a trajectory that will carry it past the outer boundaries of our solar system's gravitational influence within several thousand years before resuming its wandering existence in the true interstellar medium that fills the spaces between stellar systems. Both objects now possess sufficient kinetic energy to escape permanently from our Sun's gravitational field, joining the vast population of free-floating interstellar objects that astronomers estimate may number in the trillions throughout our galaxy's spiral disk structure. The galactic environment through which these objects will travel contains approximately 1 hydrogen atom per cubic centimeter, creating a medium so tenuous that molecular collisions occur only rarely despite the object's high velocities relative to the local standard of rest. This interstellar medium, while nearly empty by terrestrial standards, extends throughout the galaxy and provides the raw material for future star formation while gradually eroding the surfaces of travelling objects through impact processes that operate imperceptibly slowly across millions of years of cosmic time. Theoretical models of galactic dynamics predict that both visitors will experience gravitational perturbations from passing stars, giant molecular clouds, and the differential rotation of our galaxy's spiral arms during their extended journeys through local galactic space. These perturbations, while individually weak, accumulate over millions of years to produce significant changes in velocity and direction that make long-term trajectory predictions increasingly uncertain beyond timescales of several million years. The chaotic nature of galactic gravitational dynamics ensures that precise orbital calculations become meaningless over the extended durations these objects will spend wandering between stellar encounters. What intrigues galactic astronomers is the possibility that both objects may eventually encounter other stellar systems during their extended travels, potentially providing opportunities for gravitational acceleration or capture that could fundamentally alter their cosmic destinies. Statistical calculations based on stellar density and velocity distributions within our local galactic neighbourhood suggest that typical interstellar objects experience close encounters with stellar systems every few million years. Though most such encounters result in gravitational deflection rather than permanent capture into planetary system orbits, the cosmic radiation environment through which the objects will travel includes energetic particles accelerated by supernova explosions, stellar winds from massive stars, and cosmic ray showers generated by interactions with the interstellar magnetic field that permeates galactic space. This radiation gradually modifies surface compositions through nuclear reactions and chemical processing that operate continuously but slowly, creating the dark, organic, rich crusts observed on interstellar visitors while potentially destroying some of the original chemical signatures that preserve information about their formation environments. Their journeys will carry them through regions of varying stellar density, from the relatively crowded solar neighbourhood where stellar separations average several light-years to the sparse regions between spiral arms where stars become isolated by dozens of light-years of nearly empty space. These density variations influence the probability of future stellar encounters while exposing the objects to different radiation environments that depend on the proximity and spectral characteristics of nearby stars. The timescales governing their galactic wandering dwarf not only human history but the entire evolutionary history of complex life on Earth. With typical orbital periods around the galactic centre requiring roughly 200 million years to complete, during their extended travels, these objects will witness multiple passages through our galaxy's spiral arm structure, experiencing varying gravitational fields and radiation environments as they participate in the grand rotation that organises stellar motion within our galactic disk. Temperature regulation during interstellar travel depends primarily on the cosmic microwave background radiation, maintaining surface temperatures near 7 Kelvin unless the objects approach close to stellar radiation sources or experience heating from radioactive decay of long-lived isotopes within their interiors. This extreme cold effectively preserves most chemical and physical properties unchanged across million-year timescales, creating natural cryogenic storage that maintains samples of ancient planetary formation materials in nearly pristine condition despite their extended exposure to the harsh interstellar environment. The irony of their galactic journeys lies in their return to the cosmic loneliness they experienced before encountering our solar system, resuming existences of profound isolation where the nearest substantial gravitational influence may lie light-years away, and the dominant physical processes operate on timescales incomprehensible to human experience. These ancient wanderers, briefly illuminated by our sun and studied intensively by human observers, fade back into cosmic anonymity, carrying within their frozen structures the only remaining evidence of distant worlds that may no longer exist. Gravitational wave astronomy may eventually provide new methods for tracking massive interstellar objects as they interact with compact stellar remnants or binary star systems, though current detection sensitivities remain far below the threshold required for monitoring individual objects of cometary mass. Future technological developments in gravitational wave detection might enable long-term studies of interstellar object populations and their dynamical evolution within galactic gravitational fields. Their eventual fate remains fundamentally uncertain, with possibilities ranging from accretion onto stellar surfaces during close encounters to ejection from our galaxy entirely if they acquire sufficient velocity through gravitational slingshot effects around massive stars or stellar remnants. Some theoretical scenarios suggest that interstellar objects might eventually contribute to planetary formation processes in other stellar systems, delivering volatiles and organic compounds that enhance the chemical complexity available for biological evolution around distant stars. The legacy of their brief passage through our solar system persists in the scientific literature and archived observational data that document their properties and behaviours for future researchers who may develop new analytical techniques or theoretical frameworks for interpreting interstellar object characteristics. These observations contribute to the growing database of information about galactic dynamics, planetary formation processes, and the chemical evolution of stellar populations that spans billions of years of cosmic history. Statistical studies of interstellar object orbits and compositions gradually reveal patterns that illuminate the structure and evolution of our local galactic environment, providing observational constraints on theoretical models of star formation, planetary system dynamics, and the mechanisms responsible for ejecting objects from their birth systems into the interstellar medium that connects all stellar neighborhoods within our galaxy's vast spiral structure. Silence returns to the observatory as both interstellar visitors fade beyond the detection limits of even the most sensitive telescopes, their departure marking the end of an unprecedented observational campaign that documented the most comprehensive dual study of ancient wanderers ever conducted by human astronomers. The great domes housing reflecting telescopes across the globe now turn toward other targets, supernovae in distant galaxies, exoplanets orbiting nearby stars, and the systematic surveys that will eventually detect the next generation of interstellar visitors approaching from the cosmic dark. The control rooms that buzzed with activity during the object's peak visibility now settle into the quieter rhythms of routine astronomical observations, though the data processing and analysis will continue for years, as researchers extract every possible insight from the precious measurements gathered during those brief months of enhanced activity. The final astrometric positions, measured as the objects crossed beyond Jupiter's orbital distance and faded below the threshold where ground-based telescopes can reliably track their motion against background stars, establish the reference points that future astronomers will use to search for these specific wanderers if improved technology eventually enables their rediscovery decades or centuries hence. Radio telescopes maintain intermittent contact through reflected radar signals for several additional months as the objects recede toward the outer boundaries of our solar system's gravitational influence. But even these sensitive instruments eventually lose the faint echoes that provided the last direct measurements of visitors now returning to the cosmic wilderness from which they emerged. The archived datasets preserve not only the successful detections and measurements, but also the null results and observational limits that define the boundaries of current instrumental capabilities, creating a comprehensive record that will guide the development of future detection systems designed to study interstellar objects with enhanced sensitivity and temporal coverage. These archives document the subtle instrumental effects, calibration procedures, and data reduction techniques that transformed raw photon counts and electronic signals into the physical measurements that reveal the chemical compositions, orbital dynamics, and structural properties of objects whose formation occurred in stellar systems that may no longer exist. Administrative committees at major observatories begin the process of evaluating the scientific productivity and technological innovations that emerge from the coordinated observational campaigns, assessing how the lessons learned from studying these particular visitors can improve preparations for future interstellar object encounters. The international collaborations that form spontaneously to maximize observational coverage demonstrate the global astronomical community's recognition that these rare cosmic visitors represent shared scientific resources that transcend national boundaries and institutional affiliations. What lingers in the collective memory of the astronomical community is the profound realization that interstellar space contains vast populations of ancient fragments carrying chemical and physical information about planetary formation processes that operated billions of years ago in regions of our galaxy that remain observationally inaccessible through any other means. The brief passages of these two objects through our solar system provided humanity's first detailed glimpses into the cosmic recycling processes that connect stellar generations across galactic timescales, revealing how materials ejected from dying planetary systems eventually wander through interstellar space to potentially contribute to the formation of new worlds around younger stars. The mathematical models refined through analysis of these observations improve theoretical understanding of planetary system dynamics, stellar encounter statistics, and the mechanisms responsible for populating interstellar space with debris from countless worlds that formed and evolved throughout our galaxy's history. These theoretical advances enable more accurate predictions about the frequency and properties of future interstellar visitors, guiding the design of automated survey systems that will detect and characterize similar objects with increasing efficiency and scientific sophistication. Technological innovations developed for tracking and studying these particular visitors find applications in other areas of astronomical research, from asteroid impact monitoring to exoplanet detection, demonstrating how specialized observational techniques often produce broader benefits that extend far beyond their original scientific objectives. The adaptive optics systems, spectroscopic analysis methods, and data processing algorithms created for interstellar object research enhance capabilities for studying solar system objects, stellar atmospheres, and galactic structure with improved precision and reliability. The public fascination generated by these cosmic visitors contributes to enhanced support for astronomical research and space exploration programs. As the discovery and study of objects from distant stellar systems captures imaginations in ways that purely theoretical research sometimes cannot achieve, educational programs incorporating real-time observations of interstellar objects inspire students to pursue careers in science and engineering while demonstrating the international collaborative nature of modern astronomical research. The silence that now pervades observatories after months of intensive activity reflects not the absence of interesting phenomena, but the patient nature of astronomical discovery. Where significant events occur on timescales that require sustained observational programs spanning years or decades to capture the full range of cosmic processes operating within our galactic neighborhood. The routine monitoring of stellar positions, brightness variations, and spectroscopic properties continues with the knowledge that exceptional discoveries often emerge from systematic surveys designed to detect subtle changes against the apparently stable background of the night sky. Future space missions may eventually enable direct sample return from interstellar objects, using advanced propulsion systems and autonomous navigation to intercept these fast-moving targets and collect physical specimens for detailed laboratory analysis impossible to achieve through remote sensing alone. Such missions would require technological developments in high-speed rendezvous, sample acquisition, and interplanetary return trajectories that push the boundaries of current space exploration capabilities. The irony of returning silence lies in its contrast with the cosmic significance of the phenomena recently observed. As objects carrying information about galactic evolution and planetary formation processes spanning billions of years fade back into invisibility, while life on Earth continues its brief existence within a universe whose vast scales and extended timescales dwarf all human experience. The astronomical instruments that revealed these ancient wanderers now resume their patient monitoring of the cosmos, waiting to detect the next messengers from distant stellar systems that may arrive tomorrow or decades hence. Theoretical studies incorporating the observational constraints provided by these visitors begin to refine models of galactic chemical evolution, star formation efficiency, and planetary system formation rates that operate throughout our local spiral arm and beyond. These improved theoretical frameworks provide better understanding of the cosmic context within which our own solar system formed and evolved, illuminating the galactic processes that shape the chemical and physical environment from which Earth and its biosphere eventually emerged billions of years ago. The telescopes cool beneath the night sky, their mirrors reflecting starlight that has travelled across the galaxy to reach eyes that watched ancient wanderers pass through our solar system like whispers from distant worlds. In the control rooms, computer screens display orbital calculations that track objects now beyond detection, mathematical curves extending into futures measured in millions of years. The data flows into archives where petabytes of measurements wait patiently for analysis by researchers who may not yet be born, preserving in digital form the chemical signatures of materials that condensed around stars whose light has long since faded. Observatory domes rotate slowly back to their stowed positions as the night's observations conclude, their mechanical movements echoing across empty parking lots, where astronomers once gathered to coordinate the most intensive study of interstellar visitors ever attempted. The coffee grows cold in abandoned cups beside computers still processing the final spectroscopic exposures, extracting wavelength measurements accurate to fractions of nanometers from photons that bounced off surfaces sculpted by cosmic rays and shaped by processes that operated when our galaxy was younger. Somewhere beyond Neptune's orbit, two ancient fragments continue their departure from our solar system, carrying within their frozen cores samples of stellar nurseries that may have vanished eons before Earth formed. They tumble silently through space at velocities that will carry them past the orbital distances of comets that won't return for thousands of years, following trajectories calculated with precision, yet leading toward destinations unknowable. The gravitational influence of our sun weakens with each passing day, releasing its temporary hold on visitors whose next stellar encounter may occur when our own star has evolved beyond recognition. The cosmic silence deepens as distance grows, restoring the profound isolation these objects knew during their millions of years of wandering between stars. No instruments track their motion now, no telescopes gather their reflected light, no spectroscopes analyze their composition. They fade into the darkness, carrying their secrets back to the interstellar medium, ancient messengers returning to the cosmic postal system that operates on scales spanning light years and timescales measured in geological epochs. Sleep comes to the mountains, where observatories stand like sentinels watching the night sky, their vigilance unending yet patient as the universe itself. The stars wheel overhead in patterns that will shift imperceptibly across human lifetimes, carrying within their light the stories of worlds that formed and evolved and perhaps harboured life before ejecting fragments that briefly visited our solar neighbourhood. In the digital archives, algorithms continue their work processing measurements of objects that no longer shine for human eyes, extracting insights about galactic evolution from data that may outlast the civilizations that gathered it. The mathematics of orbital mechanics describes trajectories extending into cosmic tomorrows, where these wanderers will continue their patient journey through space, carrying their unalterable testimony about planetary formation in regions of our galaxy we may never visit. The profound quietude of astronomical timescales settles over the instruments and the data and the researchers who witness this cosmic conjunction, a silence that contains within it the recognition that such encounters represent brief illuminations of processes that operate continuously throughout our galaxy's vast spiral structure. Somewhere in the darkness between stars, countless other ancient fragments pursue their own lonely trajectories toward futures unknowable, carrying within their preserved materials the chemical heritage of worlds that existed before our sun learned to shine.